Okay. Yeah. So we could not continue our discussion last day due to some technical failure. I think today it is working fine. And I also uploaded lecture 2, lecture 3 in Microsoft Teams, so you can just have a look. And I am also trying to upload these lectures in YouTube. Not for all, but with some permission. So I mean for only for students of this section. So I'm trying to do that. Let's I mean let us hope that it will be done by as soon as possible. So yeah, there are some problems, but I think we'll be able to overcome. I'll be able to overcome those problems, and we'll have the lectures in YouTube. I'm trying. Okay, so last day we started talking about a problem, and then it got stuck. Okay, so let us consider the same problem. And today our plan is to discuss one of the most celebrated theorems in probability theory, one of the basic theorems which you probably know, which is called Bayes theorem. We'll talk about it in the beginning of today's class, and then we'll go ahead and discuss about random variables. Yeah, and so last 2 weeks, what we did is basically we talked about what is probability measure and different properties of the probability measure. So here today, okay, so let us start with a problem which we started discussing last day. So a problem is that we started talking about some construction work, and we say, okay, so if we start a construction, or maybe in IIT Kharagpur in the campus, if there is a construction work going on, you will see sometimes it whenever somebody is joining, please mute yourself, okay? Otherwise, every time I have to go and mute you and mute your microphone, and it will take some time. Yeah, so in the campus, you'll see that there is a expected date for the completion of a construction job, but sometimes it does not get over due to many reasons, okay? One of the reasons could be due to some strike of the laborers, due to some of their demands. So that could be one of the reasons, okay, for not completing the work in time. Okay, so let us consider a construction work, work in campus, Now it may get this, so it may stop in between and it may not finish within time. So, and one of the reasons could be the strike. So, and there is a probability that we can assume that there is a probability that there will be a strike, or there is a probability, we can also assume a probability that there will be no strike and the job will be completed on time. Okay. And there could be another thing, like there is a strike and still the construction work that can be completed on time. Okay, so let us consider all this, assume all these probabilities. So let 0.6 is the probability that there will be a strike. There will be a strike. We can assume that some other probability, like say 0.85, okay, is the probability that the construction work the construction work will be completed on time. On time. If let's say there is no strike, if there is no strike, and we can also assume that, let's say, and also assume that 0.35b is the probability, that the work will be completed, the work will be completed on time, even if let's say, even if there is a strike. Okay, now the question is, what is the probability? What is the probability that the construction work will be completed on time, let's say, will be completed on time. So this is the question. Now so our job is to find out the probability that will complete, the construction work will be completed on time. This is what we want to find out. Now, what are the given information? The given information are as follows. One probability is given to us, which is 0.6, which is the probability that there will be a strike. So this is an event. Okay, so in this situation, okay, we can consider in this particular experiment, let's say, so this can be considered as an event, okay, that there will be a strike. And we can also assume that the job will, because we need to find out whether this work will be completed on time or not, we can also assume that this is also an event, that job will be completed on time. Okay. Then here also you can see this is also mentioned that 0.85, this is the probability that job will be completed on time if there is no strike. So strike is an event, okay? Strike is an event, and this is a conditional just a minute. Yeah, so this was 0. What did I write? Maybe 35. Okay, so the thing here is, let's say we have two events. We can always assume that two events. Okay, so let A be an event, whatever it is. Let's say A be an event. So A be the event, let's say. Okay, which describes that the work will be completed on time. This is one event, and another event could be, let B be the event. So let B be the event. B be the event which describes, let's say, there will be a strike. Okay, event that there will be a strike. So whenever this problem is given to you, try to find out first that you are asked to find a probability. So given any problem, you first should denote the event of what you are asked. You are asked to find probability of an event. Okay, this is usually this will be the case. So you denote that event by some letter. Let's say A here. Okay, that this is the event A, and I need to find what is the probability of A. And then whatever the information given to you, then those probabilities which is given to you, let's say, or which are given to you, there will be also probabilities of sub events. So let us first pick some notations about those events, and then we'll formulate the problem, and then we'll see which property of the probability measure can be used, or what are those properties of the probability measure that can be used to solve the problem. Okay, this is the goal. So then what is the information given to us? B is the probability that, and B is the event that there will be a strike, and say 0.6 is the probability that there will be a strike. So that means probability of B is given to us, probability of the event B is given to us, which is 0.6. And then the next line is 0.85 is the probability that the work will be completed on time if there is no strike. So B is the event that there is a strike. So complement of B is the event that there is no strike. So 0.85 is then the probability of the event A provided complement of B happens. So then we can just formulate this as like probability of A given B complement. That means this is a conditional probability, and which is 0.85. And another information is given to you that 0.35 is the probability that the work will be completed on time even if there is a strike. So that means it says probability of A given B is equal to 0.35. So the question is, now I have to find what is, so these are all given probabilities which are given to me, and I have to find out what is the probability of A. This is what I need to find out. So how do I do that? So in this situation, you may see there are two things. I mean, can anybody tell me what is the sample space here? These are the events. What is the sample space here?
Sir, the work is done and the work
So
is
it's
not
a
done.
tree basically.
What is that?
It's like a tree, like, oh, there is a strike, there is no strike, and then in each thing there are two more options wherein completed on time and not completed on time.
Okay. So the strike consists of four possible
Four.
outcomes. That is what you are saying. Four possible outcomes.
Yes,
That
sir.
there will
Four
be
Yes,
a
sir.
pos-
there will be a strike. The job will be completed on time, and then what else?
So in the event of no strike, there are two options. It will be completed on time, it won't be completed on time. And in the absence of a strike also, there are two options. It will be completed on time, it won't be completed on time. So there are
No.
four
So
options.
so question. My question is, what is the sample space? So event I have written. You have event is like there will be a strike.
Sir,
Let's say that is an event.
A B,
Yeah.
A B complement, A complement B, and A complement B complement.
These are the possible outcomes. That's what I was saying.
Yes, sir. Hmm.
Okay. So if I say, okay, like if something happens, okay, its complement, okay, can also happen, because if something happens, if something is an event, then its complement is also an event. But here if we write like all this, like let's say this is my sample space, which is S, whatever you denote it. And if we write uh, these are the sample points, then the question would be, what is A complement? A complement should be S minus A, because if A is a possible outcome, then complement of A is the entire S minus A. So that means complement of A cannot be just a single point. It should be all the points inside the sample space except A, if A is a sample point. Because A is a sample point means
So can you
let's,
make them a Venn diagram?
yeah, so complement means what? If we write A, let's say, okay, let me make another diagram then. If this is S, if you say that A, what is A here? A is an event. Let's say I describe it an event, but suppose you consider this as a possible outcome, which is that the work is completed on time. So if this is A, then what is this complement? Its complement is whatever is there except A. Then the question will be, it is this A dot or complement of A is not just an outcome which is different from B. It should be entire thing which consists of whatever it is, the rest, everything. So this is not a good idea then, because you cannot say like A, B, A complement, B complement, these are four possible outcomes. You cannot say because A complement is a complement of A, which means it should then consist, if there is any other possible outcome like B, then A complement includes B, because A complement will be, so A is here possible. So if you want to write, like if you consider A is just a possible outcome, then you have to write as a corresponding event, let's say, because it is a set and it is a possible outcome. Okay. And if you write the complement of all possible sample points, exclude A, but this is not the case here. So you just cannot say A complement, B complement, that consists. I mean, those are the possible outcomes. You cannot say this. So what can you say about the sample space?
Sir,
Mm.
sir, can we have a Venn diagram of A and then and B, and A and B will be overlapping for some small area of the circle, and then the both of them will be enclosed in a box. I mean that the S
So,
universal set.
so you're saying this A, and there is something called, let's say, something called B. Oh, so
Uh-huh.
something is left here. So, okay, just a minute. No, then this is also in this. Also, I have to include this also. Let's say this. So this part, let's say, is something. Let's say B, and let's say this part is A. This is what you were saying.
So
Is
the figure that you have made, like it is for sure that the work will be done either on time or either late. There can also
mm,
be a possibility that the work is not done at all.
mm.
Are we considering that or are we ignoring that?
No, we are not doing that. What
Okay,
is that?
then I am saying
What,
this only, sir.
what did you ask me? What? Sorry, I mean I could not
Okay,
understand
there can
because of the
also be a
noise. Yeah.
poss. Yeah, okay, sir. So there can be
Oh.
also there also can be a possibility that the work won't be done at all, won't be completed at all. It will remain
Yes, yes, yes,
incomplete for. I
yeah,
mean,
yeah,
just so are we
yeah.
considering that case
Yes,
as
yes,
well?
yes, yes. Because see, we consider it as an event which describes that the work will be done or completed on time. So complement of A also be and should be also an event. So that means it will not be
Sir, I
completed on
think
time.
what he's trying to say is that there will be a case where the work will not be completed on time and there will not be a strike.
Yes,
But
that is the
in this
second
Venn
step.
diagram,
Oh, no, no.
there are
Oh,
rosy
okay, okay.
regions.
No, no, no.
Huh.
We'll assume that. Let's say it will be completed on time if there is no strike. I mean, there is a probability for that. Okay. So this is the information which is given to us. I mean, from the
Sir,
information which is given to us, from that we have to
sir,
consider all this. Yeah.
So
sir,
these
sir.
four
So,
regions
sir,
Venn diagram.
can we say that the A union B is equal to whole space, whole sample space? for this
You
condition.
tell me. You tell me. I don't know.
So
You
shouldn't
tell
Well,
me.
we
that's the
have more
question.
sample space left around? Like because
There is
A and
no
B eat up the
possibility
whole
the work is
sample
not
space.
can be completed if the strike is not done.
So not A, not B will still happen.
Yes, sir. Like there should be a bigger circle around this.
So
No, sir. Like
because
just
It is the bigger circle is there. Sir has just drawn with a different style.
So will there be four events? A given B complement, A given B, A complement given B, and A complement given B complement.
oh, I'm talking about sample space. So you are talking about those are the sample points.
Yes, sir. I mean, it's exactly what
Okay,
Abhinav said, but
but we
Uh,
usually we go ahead. Go ahead.
sir, sir, yeah. So there'll be four sample points, but we won't define in terms of events. We could okay by like in words. I'll put it this way. The work will the at one point work is being completed and there is no strike like that. Work is being completed. There is strike like that. And then the event A will be the 2 points. Work is being completed. No strike and strike. So just that way.
So what are the sample points here?
Uh, like say for like 1, 2, 3, 4, 1. The work is being completed. There is no strike. Work is being completed. There is strike. Work is not being completed. There is no strike. Just like that. It's just that you don't have to just the four outcomes that they were telling about, but you don't have to tell it in terms of the event. Like the sample
Okay,
points
so
you cannot say in
okay,
terms of
so
events, right? A
you
complement.
yeah, so you want to say that okay, the work will be completed on time, provided even if there is a strike, the work will be completed on time. There is no strike, and so on, right? These are the four things you are saying. I mean, these are the two things. Other two, I don't know what you said.
Work being completed, there is strike. Work being completed, there is no strike. Work is not being completed, there is no strike. Work is not being completed, there is strike. 4 points.
Oh,
Four sample
okay.
points.
Oh, okay.
And
Oh,
event A will be work 2 points. Event A will consist of two sample points. Work is being completed. Say like there is strike. Work is being completed. There is no strike.
okay.
excuse me, sir.
Yes, please.
Sir, I guess everyone is saying right, just they are using the wrong word of sample point. We can just
Okay.
consider the complete event A, like we have the
Mhm.
question to calculate that what is the probability that construction will be
Mm.
done. So we can
Mhm.
just make the whole sample space at that, and we can divide the whole space in different events of disjoint
Okay.
sets so that we can directly calculate that. Like everyone is saying right, just there's no sample point, they're the space in which the
Okay.
complete sample space is divided in many disjoint
Okay.
sets. Yeah.
Okay.
So,
So okay.
I don't know. So, like, I
I
don't
ca-
know the answer,
I'll take.
but it sounds like a bit wrong because, like, when you add the probabilities of them, they won't sum up to one, but the probability of the sample space should be one.
Yeah. Yeah. Probability the samples should be one. Yeah.
So, like, if you add the probabilities of the four events which everyone is describing, so they won't sum up to one. They'll be greater than one. So,
Yeah.
like, probably, yeah.
So those are not the outcomes. Not the possible outcomes. They are not the sample points. So the thing is, okay. Let me put it this way. The thing is, sometimes in a problem, so that's why I'm discussing this problem. Sometimes it will be very hard to write the sample space explicitly. You do not know the precise sample points, but you know some events about experiments, and from those events you have to calculate the probability using the properties of the probability measure. For example, let us say, for example, here there are four phenomena. One is whether construction job will be done on time or not. So there are two events here. Will be done or not will be done. Okay. Another thing is there is a strike or not strike. But see, apparently these two things have one can imply the other one. Okay. But as such, there is no relationship. So I can say, I can consider a particular a sample space, for example, or I may consider a sample space like a sample space consisting only of two things. One is strike or not strike. There is a strike and there is no strike. On top of that, I'll say, okay, so now I have some event. I do not know explicitly what it contains, but I'll say one possible outcome based on that. Let's say I divide the whole thing. I divide the whole thing into two parts. One is B and B complement. That's it. I have nothing. One is strike and not strike. Now there is an event here, A, let's say. The job will be done. Okay. And it can be done in time or on time, provided there is a strike or there is not a strike. And this is the probability, this is the event for which the probability is being asked. This is the event A. So I do not explicitly know what are the sample points, but I can just divide the entire sample space into two sets. Let's say B and B complements. So B represents strike and B complements does not, there is no strike. And A is something, A is that the work is completed on time, and that can have an intersection with B, meaning that there was a strike, still it is completed on time. And B complements, there is no strike, and still it is completed on time. Okay, so sometimes we do not know. The thing is, sometimes we do not know explicitly what are the sample points, but from the given information, from the given statement, okay, we have to find probability of an event. For example, here, if I consider this sample space as just consisting of 2 points, B and B complement, and on top of that, I'm considering an event which is related to B and B complement, but I do not know exactly like how, what are the sample space, okay, does this set A consist of, or whether it is itself a sample point or not. I do not know that because I cannot fit into the sample space because B is a phenomena, B complement is a phenomena. So I do not know exactly. So you can say that, okay, the possible outcomes could be complemented on time, not complemented on time. But there is another condition here, whether there is a strike or not. So I cannot just in a sample space, I cannot include all these possible scenarios, but I know that this sample space can be divided into two events, whether there is a strike, there is no strike, or the job is completed on time or not. Now, if I do this, for example, that I divide this sample space into two events where there is a strike and there is not a strike, then I'm on top of that, I'm asking this question that what is the probability of the event A, which is that the job is completed on time. Now say here, if I want to calculate probability of A, I can just say that probability of A, okay, A can be written as just I can write A intersection B. I'm just from the diagram, A intersection B, union A intersection B complement. I can just write it because it can be divided into two parts. I'm just doing set theory and nothing else. And A intersection B and A intersection complement of B, they are disjoint. So due to the postulate 3, I can directly write that this is probability, this equals to probability of A intersection B and plus probability of, because they're disjoint, A intersection B complement. Now, and if I somehow, so there is also information about this, that probability of B is given to me, probability of B, A given B complement, and probability A given B is given to me. Now, this is probability of intersection B. Now, I know the definition of conditional probability, and this can be written as probability of B because it is given to me. I want to use that information, probability of B times probability of A given B plus similar thing is given to me. I'll write now, since probability of B is known to me, I also know due to the property of the probability measure what is probability of B complement, which will be 1 minus probability of B. And then I have this probability of A given B complement. So now you see all the information which are given to me can now be used to calculate this number. So this will be 0.6 or 0.60, and A given B is 0.35, let's say, plus. This is one thing. And then plus, what is that? 1 minus this, so it will be, okay, 1 minus 0.6, which is 4. Okay, 0.4 times, what is that? 0.85. This is another thing. So then I calculate the entire probability, and it will be some value, okay, whatever it is. So here you see, I did not even explicitly know what are the possible sample points, but from the statement of the problem, I solved this. I could calculate the probability of what my desired event. Okay, just by using the information which is given with the problem. So sometimes what to happen is you need not explicitly know. You don't have to know explicitly what are the sample points, but the phenomena which is given to you, from that you can, and using the properties of the probability measure, you can calculate the desired probability. Okay, we'll see more examples, but this is an example where we use all the properties, let's say, or main true properties, or maybe let's say this is the postulate 3, P3. This is where we are using postulate 3, P3, let's say, and here using conditional definition of conditional probability, okay, or the multiplication rule which you said yesterday, last day. And yeah, so these two are the main things we are using. And here we do not know explicitly what is the sample space. We only know the sample space can be divided into two parts, with the B and B complement, or A and A complement. You can do that also, A and A complement. And then on top of that, you have a phenomena, and you explicitly do not know what are the sample points which are included in that particular event. Still, the problem can be solved. So the thing is here, most important, crucial here, the most crucial observation here. The observation here is if enough information is given to you such that the sample space can be divided, can be partitioned into events whose probabilities are known to you. This is what we used. See, here B and B complement. Okay, so B union B complement is equal to S. I do not explicitly. I only what are the sample points, but I know that B is an event, and B complement then also an event, and B union B complement should be equal to S. This is information. This is the thing which I know already. So this is called a partition of a set. Okay. So one thing is that in some problems which you will find, I mean, problem is any practical scenario, you will find that there can be a sample space, or the sample space corresponding to the problem, corresponding to the experiment. Okay. There are some events, okay, which partition that. Partition means if you have a set S, okay, this is my sample space here. The sample space can be divided into several partitions. Let's say like B1, B and B complement there in the previous example. So I can have B1, B2, B3, and so on. And partition means this subset is disjoint from this subset. And these are all events. And this is disjoint, this is disjoint, this is, so here, for example, in this particular case, B3, B4, B5. So these B1, B2, B3, B4, this form a partition of the set S. And C, probability of B1 must be equal to probability of B1 plus probability of B2, because they're all disjoint. Using the postulate 3 of the probability measure, some of the probabilities of all these events would be equal to 1, because it is a disjoint union of S. I mean, the disjoint union of the sets or of these events will give you S. So if there is a situation, okay, where you know that the sample space can be partitioned into different events, and on top of that, there is some event for which I need to find out some probability. Let's say this is my event. Okay, this is on top of that, there is an event A, okay, which can intersect some of these or all of these partition sets, okay, or B1, B2, or BIs, okay. And then my question is how to find the probability of A. Then I can use the same trick here, the way I used it here. in the previous example to calculate the probability of A. So the crucial observation here is if a partition of the sample space is given along with the probabilities of happening of those events. So this part, okay, partition. What is the spelling of partition? P-A-R, partition.
PION.
Yeah, partition. If a partition of events, let's say. Okay. So the happening of the events. Okay. So if a partition of events of the sample space is given, along with the probabilities of happening of those events, okay, then there is a way to calculate the probability of an event, okay, related to that particular sample space. This is the main observation. And so not only that, this is very, very important. And this is called the rule of, what is this? The rule of total probability. What is that? What is this rule? And this is very important rule. It says if, let's say, if there are events, let's say B1, B2, BK, which constitute partition okay, partition of a sample space S, and let's say probability of Bi not equal to 0 for all I equal to 1, 2 up to k, then for any event A in S, okay, probability of A is equal to sum of I equal to 1 to k, probability of Bi times probability of A given Bi. The proof is very simple. Proof is just this picture. See, if this is the event A, then event A can be written as, proof is very simple. The proof is like here, like A equal to A equal, the partition consists of the events B1, B2, Bk, and here let's say k equal to 5. Then you see now A can be written as A intersection B1 union A intersection B2 union and so on. Here let's say it is A intersection B5. And then the same thing, the way we solve this problem, you take the probability of A, take the probability both sides, then do the postulate tree. This the probability of A should be equal to sum of the probabilities of all these events, and then use the definition of conditional probability, and then you'll have this formula. So this is BI. Okay. This is BI. So this is BI and times this, and this is a very useful problem. So let us solve another problem so that we understand the importance of this. Another problem. Let's say, yeah.
Sir, does partition mean that it is disjoint?
Yes. Okay. So
Okay.
partition.
Yes, sir.
Okay. So let me I mean, this is again 10 plus 2, but let me define it again here. What is partition, by the way? Okay, partition of a set. So partition of a set, because sample space is after all a set. Okay, so let S be a set, then some subset, say 1 dot dot dot, let's say AK. Okay, constitute a partition of S if all this AI, they are subset of S, first of all, then AI intersection AJ, they are pairwise all disjoint, and union of this AI, I equal to 1 to K, is equal to the set itself. Just the picture, whatever we have seen in the picture, B1, B2, B5, that's the same thing. Okay, and you probably know that any equivalence relation gives a partition. If you have read about relation, equivalence relation, and all those stuff, I mean, if you can recall, then it is fine. Otherwise, this just remember that this is a partition. Partition means this is very, very important. They have to be disjoint. This is joint, and they should give, the union should give the entire set. These two things are important. So let us see another problem, okay, to understand why it is so important. And this total probability, law of total probability, another problem. Okay, so let us say that in the IIT Kharagpur, let's say IIT Kharagpur, let's say rent cars, okay, rent cars for some work, let's say, or rent ambulance, whatever it is. Okay, so let IIT KGP, so IIT KGP hire or rent, let's say, cars, okay, from, let's say, from three, let's say, from three rental agencies. Okay, now, so all these rental agencies, they have some problem. Okay, so in three different, let us say that 60% time, 60% of time, 60% of time, okay, IIT KGP rent cars from agency 1. I mean, you can take some name also because you know all these agencies, but let us write it agency 1. So that means that a car will be rented from agency 1 with probability 0.6. This is what it means, because in some problems you will see it is given in terms of percentage, but that can be converted in terms of probability. Okay, and let's say 30% of the time, 30% of the time, okay, from let's say agency 2, and let's say 10% from agency, let's say 3. Okay, there are 3 agencies. Now the problem is, let's say, if 9%, let's say 9% of the cars, 9% of the cars from agency 1 disturb, let's say, something. So you need to put some extra effort. Okay, 9% of the times, let's say it breaks down or something fails, something like that. I mean, it doesn't work properly, let's say. Okay, 90% of the time from agency 1, let's say you need to do something. Okay, it's let's say 90% of the cars from agency 1, let's say need something, let's say
Service, engines,
and
car.
what is
9%
that?
can need, sir, they can need
Can we
some
call
oiling and all those things.
Oh, oiling. Okay. Okay, some oil change maybe. Okay, some oil change. Okay, and let's say From agency 2, same problem. Let's say 20%. 20% of the cars from agency 2 to need the same thing, need oil change, and let's say the 6%, okay, from agency 3 need oil change. Okay, then my question is, here is the question now. Question is, what is the probability? Okay, what is the probability? What is the probability that a rented car, okay, given to, let's say, IRT-KGP, okay, needs an oil change. What is the probability? See, so let me explain the problem here. The problem is that IRT-KGP rents rent cars from 3 agencies, okay, and there is a probability that it may take cars from agency 1 or agency 2 or agency 3. But if so, now the thing is, these are the percentage of renting the car from different agencies. But once it is rented, that means, say, this 9% of the cars from agency 1 needs an oil. That means if the car is from agency 1, then okay, so if you 100 times, if you rent a car from, maybe 100 cars if you rent from agency 1, then 9 of them need oil change. Okay, if you 100 cars IRT-KGP rent from agency 2, then 20 of them need oil change, and so on. So this is conditional. This probability are conditional probabilities. Okay. Then the question is, what is the probability that if you rent IRT-KGP rent a car and that needs an oil change? Because that need not also need an oil change. But what is the probability that it will need an oil change? So now, if I want to answer this question, so whatever the probability is being asked, I always have to assign an event corresponding to that. So just without looking at anything, you can always define an event which is event in question. Okay, so you can always select, let A be the event. A be the event that the car which is rented, the car, okay, needs an oil change. You can always say this, that this is my event for which I want to calculate the probability. Now, what is given to me? That the car can be rented from agency 1, agency 2, agency 0. Based on that, I can define my events. So let's say, now here you see B1, B2. So I am denoting this with a purpose. B1, I'm denoting this events with a purpose. B1, B2, B3. Let this be the events that the car comes from okay, agency 1, 2, okay, or 3 respectively. Okay, now what is given? That 10%, okay, so 9% of the times of the cars from agency 1 need oil change. So then what is given to me? What is given to me? 3 things. First of all, given to me, what is the probability that IRT-KGP will hire the car from agency 1? This is given to me. What was that? 0.6. 0.6. probability of B, that means the car is higher from agency 2. So probability of that is 0.3, 0.3, and probability of B3 is equal to 0.1. These are the things which are given to me. Now, if I hire the car from B1, and this is the agency 1, so B1 has occurred, then what is the probability that it will need oil change? This is given to me, which is 9% of the time, so the probability is 0.09. Then probability of A given B1, B2 is like 20% of the time, so it is 0.2. And probability of A given B3 is 0.06. These are all given to me. Then what is the question? Question is I have to find what is probability of A. Now see here also the same thing. I do not explicitly know what is a sample space. I do not know, but I know that the sample space means what? It consists of possible outcomes. What are the possible outcomes here? That I could, IIT KGP could rent a car from one of these agencies. Okay, guys, some of you probably are writing me messages. I cannot see it. Okay. So now what I'm doing here is, yeah, somebody says mutually exclusive and exhaustive. Yes, this is what it means by partition. Yes, exactly. Yeah. So probability of A, then so I can write like this. This is my sample space, and here are 3 events. One is B1, one is B2, one is B3. That means I hire IIT KGP hire or rent some cars from one of these 3 agents. And on top of that, I have an event, let's say, which is some A, that there is a car is rented from one of these agencies and it needs an oil change. Okay, so then I just directly use the formula, okay, from this total law probability. So what will be the formula? It will be just directly use the formula because it is on the same problem. So sum of this probability of BI times A given BI. So that means here it is probability of B1 times probability of A given B1 plus probability of B2 times probability of A given B2 plus probability of B3 times probability of A given. And then you just put all the values because all the information is given to you. All these values are given to you. So you put all these values here and find out the answer. That's it. Okay.
So,
Yeah,
hello.
please go ahead.
Sir, I had 2 questions. First, in the theorem total probability, is P of BI not equal to the necessary condition?
Yeah, so why? Because see, if BI probability of BI equal to 0, then it is not a non-trivial event. Because event not equal to, if it is a 0, I mean, it's probability 0, that means we always assume that the probability of null set is equal to 0. So I'll not go into, discuss more about it. When this question is, can there be an event which is not null and its probability be 0? Okay, there can be. Okay, there can be events. But then that, so this will not fit into this particular situation. Not only that, so this formula, whenever we use this conditional probability formula, we always assume that if we assume that, like, whenever we talk probability of A given B, we always assume that B has occurred with non-zero probability. That means probability of B is not equal to 0. Okay, if you see, whenever we define conditional probability, we assume that this probability of B is not equal to 0. So whenever we are writing this term, probability of A given B1, it means probability of B1 is not equal to 0. That's why it is necessary. Okay. So yeah, so I mean, I mean, there is a, I mean, I can talk about it a little more, but the problem is, okay, so let me say a few words about this thing. My question is to you is, let's say I'll give you a food for thought. Okay, my question to you is, suppose consider the same problem. You so let's say you notice a particular region on the wall okay, of the room you're sitting right now, okay, you assume a particular region. And then you assume that you want to throw your pen on a particular point, okay, inside that region. Now, if I ask you the question, what is the probability that your pen will hit on that particular point? What is the probability of that? Okay, what is the probability that it will hit on that particular point?
Depends
This is
on
my
my
what is that? What is that probability?
sir. It depends.
0.
0. But
It's
see
a
here, you accidentally you may hit the point as well. When you throw the pen, maybe it may hit that point also. So will it be correct to call that probability of that will be equal to 0? So this is just a food for thought. I mean, this is just a question, you think about it. Meaning, what I'm trying to tell you is, why I'm saying is, in 10+2 level books, you'll find that an event with probability 0 is called an impossible event. Okay. So the thing is, I mean, that will not going to occur. Okay. This is not possible to occur. Let's say that's how they probably explain. But questioning here is, I gave you an example where this could also possibly occur, and you are still saying that it could be equal to 0. So which one is correct?
Sir, it's not
Okay.
0. Because the tip of the pen, for example, isn't one point, it's an area with some small area. So
Yeah,
the
no,
target
no, 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 no. I am saying just a
Sir,
point which is very,
sir,
very tiny, which is very, very tiny. Suppose your pen is, let's say, is very, very thin. I mean, let's say on the so on the tip of the point, whenever you are writing the pen, okay, in the refill, so that the top point of that will hit that. I mean, it is a very, very tiny point. I mean, it almost does not have an area, let's say, okay, our area is very, very small, let's say, and you have so many points you can. I mean, we'll not discuss about this, okay, we'll talk about this maybe later. But I am just asking you a question. You think about doing it and come up with an answer. Maybe we'll discuss it next day or maybe sometime later. Okay.
oh,
Yeah.
and
If you have any question regarding this
sir.
question, you can ask me. Yeah.
so it's a
So
slightly
can we
different
say
point, but
that it's happened, but we cannot see?
No, I don't want that kind of an answer. Okay. Because it is mathematics. So whatever your
So
answer is, that has to be explained. Yeah.
then we will go to quantum mechanics, then happen and cannot see and all those things.
Yes, sir.
No,
We need a
whatever.
microscope to see the event, sir.
Okay. So whatever you want to answer, you think about it and give me a possible answer maybe next day or some other time. Okay.
sir, as a different question. Back in the case when we were constructing the sample space for the event in which there's a strike and whether the work gets done or not. So the shape that you did construct was topologically equivalent to a Venn diagram inside a larger sample space.
Mm-hmm.
So then why was the original Venn diagram incorrect?
Which one? Here.
No, sir, about this.
About the problem, the region I said.
No, sir, the one about the worker strikes.
Yeah. What is your question?
Sir, in one of those, like me and a couple other students suggested a Venn diagram inside the complete sample space.
Mm-hmm.
So in the final thing that you constructed, in which you divided the sample space into two and then drew A on that. So this is still topologically equivalent to a Venn diagram.
No. Forget about what do you mean by topol. Okay. So
Sir, as
what I'm
in,
trying to. Yeah, please go ahead.
sir, as in all the regions are the same. Like even if you want to split B into 3 or 4 events, you can still do so in a Venn diagram.
Yeah. So this is a Venn diagram. Whatever I have drawn, I did not say that it is not a Venn diagram. What I said is, you may not know explicitly what are the sample points, but you know, I mean, enough information is given to you such that you know that the sample space has a partition. So there
Sir,
are
that's
two.
all right, but why was it incorrect?
What is that?
Sir, I got that point, but why did you say that the Venn diagram was incorrect?
Which here?
Yes, sir.
No, I didn't say it is incorrect. I am saying that
Sir,
you
it's been multiple times, and like every time you didn't accept it.
No. Oh, your sample. So your example, I thought whatever I had drawn here, B and B complement.
No,
No.
sir.
Your
Sir.
example. You gave that example. Your answer, you are saying.
Yes, sir.
Okay. In that answer, if I remember it correctly, one sample point was there, and its complement was there also a sample
No,
point.
sir. I
There are
mentioned
other.
just a Venn diagram with A and B as separate intersecting circles.
Like sir, in the square separator, there are inside two circles with the intersecting in some regions.
No. See. The thing is, if you say like this, okay, we'll not spend much time on this, but let us say this. If you want to say this, you want to say this. This is A and this is B.
Yes, sir.
Okay. So the thing is here, what do you mean by this? B is a phenomena which is that there is a strike, and A is a phenomena that work is done. So what are you saying exactly here? What are your sample points? I mean, what are the possible outcomes here?
Sir,
In this diagram, I think, sir, the problem is that when the B is not happen, then still there is chance the A can be happen. So the B
That
complement is also include the A.
Yeah. B complement. I mean, B complement is S minus B. Yes. B complement is there is no. Well, somebody's
Sir,
here.
this diagram is exactly.
Yeah.
Sir,
Tell
Yes,
us.
sir.
these
This
two
is the same
diagrams
diagram.
are exactly the same, na? Yes, sir.
Yes, sir.
It
No.
has B and B complement as well as it has A and A complement.
Yeah. No, but if you say this, there is a point here. The thing is, if you say this, that S is a subset, A is a subset of the sample space, B is a subset of the sample space. Now the question is, what do you mean by those subsets here? What I said is, A is an event, let's say, which is completely different. You do not know what is there, what is not. You completely do not know. But I'm saying that you focus on B and B complement, which actually partition says, because B is related to B complement. For example, in the next page, when we discussed about B1, B2, dot, this thing, so they are all related events which constitute the sample space. On top of that, so whenever you write this, for example, on top, or let me complete first. So on top of that, whenever you consider a phenomena, which can appear, which can have non-empty intersection with B1, B2, whatever the event, the corresponding sets in the partition. Okay, then what you are considering is that particular event is on top of that. So the thing is, there is a context. There is a context which is like B1, B2, BR or BK, which gives a partition, which gives a considerable partition of the set S. So this is the set of context. On top of that, you are considering an event. But whenever you say, so is this picture and this picture, apparently they are same. But what I'm saying is, when you try to explain it, so when you say that, I mean, let's say, I would say, I mean, I'll give you a different example. For example, let's say a set of sample points. Okay, let's say it consists, we are talking about, let's say, some apples, and you have also some oranges. Okay, now, I mean, the thing is, A and B, they are not in the similar context. This is what I'm trying to emphasize. Pictorially, it may be same, but whenever you try to explain, so whenever the possible outcomes, they are related to a particular context, and that thing is not there. Whenever you say A and B, they are sample points, or they are events corresponding to that. I'm saying that you don't go into that. Based on the context, you set the sample space. On top of that, you consider an event that is related to that particular context. I mean, did I make any sense?
Yes,
what
sir.
I'm trying,
Yes, sir.
what I'm trying to tell you is that there are two, three maybe different distinct things. Okay, do not put everything in a sample space. What you see, it set the context, and then you see what are the possible events which can possibly give you a partition of the set, and then on top of that, you consider whatever the events you have, and then see whether there are any non-empty intersection or not, and then calculate this way. But if you go from the beginning itself, you can probably do it. But the thing is, whenever you have a sample space, you have different things which you put together as a sample point, possible sample. I mean, let us say, what do you mean by sample point? That is a possible outcome. If I say the strike is a possible outcome, work job is possible outcome. I mean, these two things are not matching. I mean, not in the similar context. That is what I'm trying to tell you. Okay, but if you say strike, or not strike, then these are in a similar context, in the same context. The context is the same. This is what I'm trying to tell you. But anyway, yeah. So otherwise, if you want to explain it this way, you can go ahead. But the thing is, whatever I said, that will be easier to explain things like sample space is sample space of corresponding to an experiment. Okay, whenever you describe that, so you fix the context. What is the context? What are the possible outcomes? Okay, whether that gives you a partition or not, and then possibly you can use these formulas. Yeah.
Sir, by context, you mean that, like, for example, we computed that the probability that the construction would be completed. We could have also computed the probability that there would be a strike, given all the
Yeah, yeah,
PAs
yeah.
and related stuffs were given. So we are actually constructing layers, and I mean topologically layers on top of layers to cover
Do
the
not.
sample space like that.
so
I
so
mean,
do
just
not.
in a very
No,
vague
what I'm
language.
saying here, no, what I'm saying is, I mean, do not bring topology into here, but what I'm trying to tell, just a minute. So, yeah, so in this picture also, you could have written like this. You have A and A complement. That is also a context, that it is complete, the job is completed on time or not. This is also a context. And then is on top of that, you can say there is possibly a strike, which is B here, That also you can say. But so what I'm trying to tell you is that you set the context, and based on that, you divide the sample space.
Accordingly calculate and do the
Yeah,
mathematics.
yeah. Because if all the sample space is all possible sample points, they are mixed up, then there will be, I mean, okay, you can possibly do it for this problem, but whenever you have many contexts, okay, and then there is a chance that you will mix up situations. So it's always better to fit it in a particular context whenever you have the sample space. Yeah. Okay. So maybe we can elaborate more on this, but we are running out of time. So, okay, now we'll, using this total probability, I mean, using concept of this partition, we have the most celebrated theorem, which is the Bayes theorem. And probably in your entire life, if you are in academics or in industry, sometime you have to use this theorem. Okay, this is so fundamental, though so simple, but so fundamental. Okay, this is the Bayes theorem. I mean, there will be many occasions where you will see that there is a Bayes theorem, which is hidden inside. I mean, ultimately, you have to use the Bayes theorem after constructing all the problems. So this is very, very fundamental theorem. I mean, there will be problems everywhere which need to use this theorem to solve those problems. So this is called Bayes theorem. It is simple. Whatever we have discussed, from that we can state this theorem. And proof is very, very simple. Actually, we discussed the proof already, actually. But anyway, so let us write the statement. So let's say if some B1, B2, let's say some, whatever we have written here, partition, BK, okay, BK, B1, B2, BK, okay, form a partition of, okay, of a sample space S and probability of Bi not equal to 0 for all I less equal to 1 is equal to K, then for any event A, with probability of A not equal to 0, this is the statement that BR, let's say given A, is equal to probability of BR times probability of A given BR, and then summation I equal to 1 to K, probability of BI and probability of A given BI. This is very important. I'll tell you, actually, whatever we discuss here, the Bayes theorem addresses the converse problem. Okay, and what? Okay, the proof is very, very simple, by the way. Proof is proof is probability of you just use the formula of conditional probability, which is probability of BR intersection A divided by probability of A. And probability of A is actually, so here you see this S is by given this partition, okay? B1, B2, all this thing. So this is S. And probability of A, and A is an event which is on top of this partition. So A is somewhere here. Okay, this is what is A. Oops. So this on top. So this is what is A. Okay. And probability of A in the denominator, this part is already actually discussed here in the total probability, rule of total probability. This is what is there in the denominator of the Bayes rule, Bayes theorem. So it is here. So this part already know. So from total probability formula, total probability formula, and of course the numerator is nothing but the conditional probability. Here you can write this as probability of BR, just the conditional probability definition, A given BR. Okay. Now here, why I'm saying this addresses just the converse problem, the inverse problem, let's say. Earlier, what we considered, okay. For example, I mean, we can consider this agency problem, let's say. Here, what did we ask? So the question was, what if a car is rented, okay, then what is the probability that the car needs an oil change? If I so if this was the event, A is that it needs an oil change. But if I twist this question, let's say the car which is delivered, I mean, which is rented, it needs an oil change. This event has occurred. But now my question is, from which agency has it been rented? So from which agency, okay, does it come from? If that is the question I ask, then actually I'm asking this probability that this event, let's say here, it means the car needs an oil change. Now, what is the probability it came from B1, B2, or B3, the agency 1, agency 2, or agency 3? Okay, then this formula addresses that problem. And everything is known here. Everything is known here. Because this is, I mean, the same problem, if we consider all the other information is known, all these other values are known. So you can use this formula, but my question is changed now. So the question is, A has happened here. Now see the picture. During the total probability, we were asking what is the probability that A will happen. But here, A has already happened. But the question is now from which BI, through which BI A has happened. Because A can happen and B1 also can happen. B2 can happen and A also can happen. B3 can happen, A also can happen. But suppose B1, you know that A already has happened. But the question is with which BI the intersection is on. So that means basically the Bayes theorem also can be understood using this very simple 3-step diagram, which is, let's say, something, okay, that something about S, let's say, then it can occur, okay, with, let's say, B1, it can happen in B1, it can be in B2, and ... it can be in, let's say, some BK. And if B1 has happened, then there is a chance that A also can happen. So this is, let's say, A has occurred, B2 has occurred, then A also can occur. So A can occur through B2, A can occur through B1, A can occur through B2, and then these are the probability that A will occur given the fact that B1 has occurred. B is a probability that A will occur given that B2 has occurred. And this is probability that A will occur given that BK occurred. Okay. And yeah, and then what is the probability that A will occur? Then this is probability of B1 because it has to occur first. So this is probability of B1. With this probability B1 will occur. With this probability B2 will occur. And with this probability BK will occur. So A will occur through B1 means it will occur with probability this probability of B1 times probability of A given B1. So A will occur with probability, I mean through B2 with probability of B2 and then probability of A given B2. I mean it has to come through this from this point, this origin. It has to come through either B1. I mean A has occurred, but it has to occur through B1 or B2 or BK because A has, you see the diagram here, A has a non-intersection with all these BIs or at least some of these BIs. Okay. Then whenever A occurs, then you have the probability, the question in the context here is with which BI, through which BI A has occurred. That means A can occur if one of these occurs, B1, B2, BK, but which BI occurs, which guarantees that A had occurred. Okay, and this answer can be given using the Bayes theorem. So one hint is, so one problem here is, okay, in the agency problem, let's say, let me just write it. In the agency problem, if my question is, what is the probability that the rented car, okay, the rented car needs an oil change, okay, and let's say, okay, let me reformulate. What is the probability that the rented car, which needs an this came from, let's say, agency 1. That's the question, and this question can be answered using just this formula, this Bayes theorem. So my suggestion or advice to you will be, whenever you see a problem where the sample space can be partitioned into different events, you always think that there is a need to use Bayes theorem. So understand the problem and see that when the sample space, whether enough information is given to you to partition the sample space, okay, and the corresponding partition sets like B1, B2, BK here, you know the probabilities. In that case, in most of the time, Bayes theorem can be used to solve that problem. Okay, so given a problem, you always first check out whether the sample space can be partitioned. Okay. Now, so this is the module 1 of the course. So we have completed the module 1, which we are supposed to do by last week. But anyway, that is not a problem. So now we'll start a new topic, okay, to deal with this kind of a problem, okay, more math in a more mathematical way, okay. We'll talk about that, okay. So we finishes the module 1. Now we'll start talking about which is called random variables. Random variables. So the reason, okay, why we need to use this, or why do we need to learn this? Because the thing is, here I must tell you this thing, that there are many experiments, okay, where you actually do not know all the sample points because they are not given to you. And there can be many possibilities. It is very hard to explicitly write the sample space. It is not possible, okay? But there could be enough information, okay, known to explain the sample space. So you cannot explicitly constitute the sample space because you do not know explicitly what are the sample points, but you have an idea about the sample space, okay? And from that idea, let's say, you can solve some of the problems, okay, related to that experiment. And random variable is a concept through which you reformulate your problem, okay? I'll give you a scenario. For example, if there is an experiment which consists of billions of sample points, okay, so it is not possible to write all the sample points. And let's say, I mean, if I ask you, write all the words, English words in the English dictionary, okay, there are so many words you can write all, and then you calculate probability of particular word, okay, in a particular context. So it is not possible, okay. Then what do you do? Whenever you have this kind of a situation, the outcomes are very complex, they are very abstract. So you convert them into numbers, but you associate numbers along with that and see the properties of those numbers. I mean, all the events. So the goal of the random variable, let's say, or the, let's say, the objective of random variable. Okay, what is the objective here? The objective here is associate numbers. Numbers means here real numbers. Okay, let's say real numbers with possible outcomes. And formulate the desired events okay, through this association. Now what do I mean by this? Association of the numbers. So what I'm saying is, let's say head and tail. Okay, I mean just a simple example. Or let's say you have all the 52 cards. Okay, now we have different cards. Okay, but let's say most of the cards have numbers, like 1 2 3 4 6 10, okay, 9 10, and then you have queen, you have king, and you have something else. Okay, so let's say I also give numbers to the queen, to the kings, and then desired event means what? Whenever I'm associating numbers with the possible outcomes, then I have to explain all the events, which is a collection of the sample points, okay, using those numbers. And then once that is done, then I can play all possible things with real numbers. So I can play all possible things directly with all the events. Because I know the real numbers very well. I know how to deal with real valued functions very well, and to use that literature to solve problems in probability by associating outcomes with numbers. This is one of the first goal. So formulate the desired events means explain the events through the numbers which corresponds to the outcomes or the sample points. Or the sample points. So this is the main objective. Okay. Now I'll start with an example. Okay. Let us say I have two die. Okay. So one is, I mean, how to associate numbers? You can associate arbitrarily, by the way. I mean, we do not right now do not need to go into the depth. Okay, like what kind of, so basically what I'm trying to tell you here, association means then, so let's say you have a sample space. Then if I say X is a random variable corresponding to this sample space, that means X is a function from this. It's a real valued function. For example, if S is, let's say, head and tail. So instead of writing H and T, I'll write, let's say, X I'll define from S to R as X of H is equal to anything you want to write. Let's say 2 you want to write. And X and T will be equal, let's say 1. You want to write. No problem. You can write. Or maybe you can write X of H equal to 0. X of H T is equal to 1. No problem. But we will see later on that depending on the context, the random variables have to be defined properly, otherwise there will be problem. Okay. I mean, for the sake of theory, we can say, whenever I'm saying what is a random variable, I say, okay, it is any function you define, I don't care. But when we'll solve problems, you will see when consider examples that depending on the problem, depending on the context of the problem, I probably have to define a random variable, which gives meaning to the context. Okay. For example, let's say I throw a pair of dice, let's say. Okay, I roll a pair of dice. So let's say another. So this is one example. Another example, let's say, roll, okay, a pair of dice. Now, what can happen? So I can have these possibilities. Let's say this is one. This let's say I have two different dice. Let's say one is a red dice. So this is a red die, and another one, let's say something else. Let's say a green die. So this could be 1, 2, 3, 4, 5, 6. And also this could be 1, 2, 3, 4, 5, 6. So when I roll a pair of dice, what I can have? Like both can be 1. This could be a possible outcome. This could be a possible outcome. 1, 2, 1 or 1, 2, depending on what I consider it die as the first die or second die, doesn't matter. Then this could be all these grid points, they could be possible outcomes. Okay, now once we have all these possible outcomes, let me just write it down explicitly. What is it? So these are all the points. My drawing is very, very bad. Now, suppose these are the possible outcomes. So I now want to associate numbers with this outcomes, possible outcomes. Now let us say, okay, I can do it arbitrarily, but let us say I define a random variable, which is a function from S to R, and here S is the outcome of pair of the dice. Okay, it could be both 1, 1, and let me write it as 2. 1, 2, let me write it as 3. 1, 3, let me write it as 4. So I am just assigning values to possible outcomes. This is, let's say, 5, 5. This is, let's say, 6. This is 7. Again, this is 3. This is 4. This is 5, 5. This is 6, and so on. So this is 8, and here let's say it is 12. It is 11. Here it is 11, and so on. So this is my random variable. I am just assigning some values. Okay, I will. Okay, you can define it in a different way, not a problem. But why did I define it this way? I'll tell you a little later. Okay, but I'm just giving an example. Okay, that this is a random variable. You can assign it different. But here, how did I assign it? I said S of, let's say, SR sample points, and let's say SG for the green die. This is the outcome. Then I am writing it as SR plus SG. That I'm just adding it up, and that's how I am defining that the value, the real numbers, which correspond to the pair outcome of the pair of the die. Okay. So formally, let me define what is a random variable. This is an example. I will come to this example later on. So, but let me just formally define first what is a random variable. So if S is a sample space, or S is the sample space, okay, S is the sample space, and okay, or it's sample space corresponding to an experiment, then x, or then a function x which is from S to R, okay, is called a random variable. Okay, now you may ask me very many questions. For example, what kind of, I'll just say any function. Can any function be a random variable? Okay, my answer will be no. Any function need not be a random variable. Okay, then the question will be what kind of function will be random? For example, if I consider a constant function, can it be random variable? I'll say okay, it can be random variable, but what will you get out of that? You can define all the outcomes to be same values. Okay, let's say each head and tail. For head you denote it 0, for tail also you denote it 0. Then the question would be, how do you explain all the events using these numbers? Because you have two different outcomes and you associated both the outcomes with a single number. Then how do you deal with that? I mean, what is the use of that outcome? What is the use of that random variable? See, my goal is to calculate probability of an event. And I want to explain the events using this function, using this random variable. And this random variable is not a variable. It's not random also. It is just an association of outcomes of an experiment. Okay. Then the question here is, if it is an association, it is a function, what kind of association it is? Now, my one line answer is, it depends on the context. How to define this random variable? Okay. If you want to go into mathematics, if you want to study mathematics, then formally it can be defined by a measurable function, but I am not going into that details of this. I mean, what I mean by this, I mean, see here probably you make a guess what kind of functions could be possibly a random variable. Let me give you the guess. So this is a hint to answer this question. I will not discuss this because it is not required in your course. Let me give you a hint. So this is the set, okay, of different sample points. Okay, and let us say it is a discrete random variable, or let's say my number of sample points is countable. Okay, my sample space is countable. In that case, I'll call it a discrete random variable, by the way. And what I'm associating this with, I'm associating this with numbers like 0. It could be positive, negative. Now, if I want, so this could be, let's say my x, this function. If I want to associate events with this, then probably I have to explain events using this function. Then probably what I have to do, once I define these numbers, whatever the numbers I define on the real line, okay, doesn't matter. And probably the numbers I define here, I have to take the inverse image of that particular number or that particular subset of R in order to construct my events. Meaning, let's say I have some X here. I consider X inverse X. What do I mean by this? This is all sample points in S such that X of S is equal to, let's say, X. And then I can possibly say whether this is an event or not. If this is possible, meaning for any such X in the real line, okay, corresponding inverse is an event, then that function will be called a random variable. Okay, because I want to explain all the events through this function random variable, and this is the only way to do it. So then the question is, what kind of function will have this property and so on. So I'm not going into that. Okay, then I'll answer this. I mean, if you are interested, you can search for it. There are something called measurable functions. Okay, now what is measurable and other things that I'll not explain here because it is not required in your course. But I'm just giving you a hint that what could be the possible answer. Okay, so this is a random variable. So this is an association with sample points to real numbers. That's it. Now see here. Now let us go back to this example. When I say this x, if I just write x equal to 9 or x equal to 5, okay, now you consider this example here. If I, so this is, you already have noticed how did I define my random variable. Now if x, this small x is equal to, let's say whatever you want, let's 5, okay, then I will denote x equal to x. This is very dangerous notation. You see here, capital X is a function, small x is a number. By this, okay, by this, what I mean is that capital X equal to small x, which is, okay, let's say, which is 5 here, which is 5 here. By this, what I mean is that all those sample points in S such that x of S is equal to 5. Same inverse. I'm denoting instead of writing it as in. Yeah, I'm saying instead of writing this inverse, I'm introducing a new notation. If x equal to 5, x is what? X is in the, you see, this is in the real line. Okay, given any point in the real line, I'll say x equal to 5. I'll explain this as an event. X is a function from sample space to R. Now I am describing now events of the sample space or subsets of the sample space through this function x. And how I am doing it, I'm saying you give me any real number like x here, you give me anything, then I will say capital X equal to 5 if our capital X equal to 5 is the event given by this or defined by this set of all sample points for which value of x of S is equal to 5. So this is the meaning of this entire thing. This corresponds to the event this. X equal to 5, this notation means this. In fact, if you would ask, right, x equal to a, where x is the random variable, this corresponds, this is the association, corresponds to the event, all sample points, okay, such that value of those sample points is exactly equal to a, where a is a real number. Now see here, in the previous example, if I just say x equal to 5, what is the corresponding events? If x equal, then in the previous example, let's say, in the previous example, x equal to 5 corresponds to the event. See, my definition was sum. So it could be 1, 4, it could be 4, 1, it could be 2, 3, it could be 3, 2. And this could be an event. Because this is a subset of the sample space, because sample space consists of all these points. Okay, it's a pair of outcomes of red dye and the green dye. So once I define this x equal to 5, let's say if I write x equal to 9, then this corresponds to the event, let's say I can write 3 6, okay, 4 5, 5 4, 6 3, and this is of course a subset of the sample space, so this corresponds to the event. So my goal was, so why did I introduce this concept of random variable? To associate events through numbers. Okay, first my goal was to associate sample points with numbers, then using those numbers I am describing the events of the experiment. Here my experiment was rolling 2 dice, a pair of dice. One was red, one was green. Once you roll 2 die, okay, 2 dice, then what happens is in this dice there will be some outcomes. Let's say in the red die 1 occurred, and other one, the green one, 5 occurs. Now how did I define my random variable? You could have defined the random variable in a different way. Instead of, let's say, plus this, you could have done is minus this, anything arbitrarily also you could have done. Okay, no problem. But once it is done, then corresponding to any real number, for example, if I say what corresponds to this, what event, I'll say this is a null event because there is no sample point whose value of x will give you 0. Then this corresponds to the event phi, null set, because no value 0 is not taken by this function x here. See, I define this x as sum of the outcomes. So it is not 0 is not taken by this. So even if you define a constant function, theoretically speaking, constant function means, let's say, for all the outcomes, you fix a number, let's say 2, or maybe something like 100. Then you see, except 100, all events cannot be achieved by this random variable, except entire sample space or the null set. No event can be achieved by a constant function. So whenever you are defining a random variable, okay, so it has to be meaningful. It has to be at par with the, it has
Sir,
to be
can you
related.
repeat that?
Okay,
In,
so what I'm saying, okay, what I said is
that's
the following.
sample space and null space thing.
Yeah,
Constant.
okay. If the random variable is a constant function, for example, x s to r is defined as x of s equal to, let's say, 100 for all x in s in the previous example. Of rolling a pair of dice, then for any a is an r, okay, x equal to a corresponds to the event null if a is not equal to 100, and it corresponds to event s if a is equal to 100. Because for all sample points, okay, this value is 100. Otherwise, it is not taking any value. So if we write a is equal to, let's say, 5, so then x equal to a means what? All the sample points for which the value of x is equal to 5. And there is no such event because the function is defined as this way, equal to 100. So either you will get null set or the entire sample space. So there is no meaning. Although it's a valid random variable.
Just depends on our, what we decide.
Yeah. So depending on the context, that's why I'm saying, depending on the context, you have to define random variable. But any function can be can be called as random variable. Whenever I say any, this is actually any at your standard, let's say. Okay, it cannot be any because that's why I said like it is a measurable function. So it has to have some properties. Well, let's say for your standard and undergraduate standard, your course standard, let's say, it could be any function, okay? Like whatever you can think of. Okay, so you can associate. So the ultimate goal is to associate numbers with the sample points depending on the context. This is very, very important. So the objective, let me write it down. The objective of, and this is how, see, the events are associated. We just write a number here, then the events will explain by x equal to 9, x equal to 5, x equal to anything, like here, x equal to 0. You can write x equal to 100, 5, whatever you want to write. Any real number you can write, and then it should give you an event. This should be the property of the function. The objective of defining a random variable is to explain the events in terms of this function, x function of a real valued function. Real valued function. In fact, you will see later that later means later in the course, okay, that we don't care about sample space. We don't care about knowing the sample space explicitly. We don't care about knowing all the events explicitly. We only care about random variable. If the random variable is given to me, I can explain all possible things about the experiment through that random variable. Why is that? Because, for example, let's say, suppose if we have a sample space consisting of 100 points, then how many events can it have? It can have 2 to the power 100 events, because any subset of the sample space is an event. And if this sample space contains 100 points, 100 sample points, then how many subsets does it have? It has 2 to the power 100 subsets. That many events one cannot consider. Okay, and if the sample space, the size of the sample space increases, then the number of events exponentially increases. Okay, one cannot deal with that. So everything has to boil down to a random variable. Once a random variable corresponding to the experiment is given to you, everything about the experiment is given to you. So this is the main thing actually. If you know the random variable, then we'll analyze the corresponding experiment. This is the first step. We explain the events. Now we'll talk about how to discuss probabilities of the events. That means our next goal would be So our first goal we achieved. We explain some of the events by x equal to a, writing capital X equal to a, let's say. Next will be how to define, let's say, how to find probability of x equal to a, or how this can be defined, how to find this, let's say. This is the question, how to find this. But in fact, this is the wrong question. In fact, whenever we'll see later on, because today our time is almost up, later on we'll see that if this is given to me, that means most of the things about the event, about the random experiment is given to me, using which we can solve a lot of problems. And this is very important. This is actually called a distribution function. Distribution function of the random variable. We'll talk about that tomorrow. Of the random variable. So random variable is a very important concept. In fact, this is entire probability theory, statistics, everything depends on random variable. Gradually you will forget about sample space because you don't need it. Where sample space could be very, very huge. All events could be very, very huge, that size. Number of events could be very huge. We don't need it actually. We only need how this function is defined, or can I guess this is how what is the value of this function? Okay, what is the value of this function means if you consider probability as a function, then we can write probability of x equal to x, then this will be a function of x. Then how to get it? Okay, if this is given or this is not given, then how to approximate it and so on. And this is the main thing about probability theory. Okay, so we will discuss about this next tomorrow. Okay, we'll start discussing about this tomorrow. We'll define some of the important. We'll see for some of the examples about this random variable, and then gradually discuss many things about this. Yeah. So if you have any class, then you can leave the room.